Anybody with us today was not with us yesterday. You need this stuff. Now, I'm sorry to say that due to my lack of paying attention to matters at hand, if you try to view the video for yesterday's class, you'll have the pleasure of going back to the 1910s and 1920s because it'll be a silent movie. I forgot to check the batteries in my microphone. That's been fixed. Today, as you, I should imagine, would expect, we shall proceed with our introductory considerations regarding equilibrium. Important? You betcha. Because, as we noted, equilibrium is the most stable thermodynamic state in which a system can exist, like a reaction system. And under particular conditions, every reaction can be made to achieve equilibrium. Upshot, we need to understand equilibrium, particularly because if, for example, you need to make B by starting with A. You start with a mole of A. Your job, because the boss has said so, is to make a mole of B. So, if you begin with a mole of A and apply to it appropriate conditions and begin the conversion of A to B, you're on your way. But what guarantee do you have that the mole of A is going to turn into the mole of B? You don't have any. And what do you have to know about the possibility of converting a mole of A to B? You have to know about equilibrium. Because if, for example, this reaction goes 50% extent, and then the equilibrium condition is established, how much B do you wind up with? You start with a mole of A. Let's get this one out in front of there. You start with a mole of A. You got no B initially. Your job is to make a mole of B. So you place A in the environment in which the conversion of A to B takes place. But under these conditions, which are the best conditions that can be achieved, this reaction goes to an extent of 50% as written, and then equilibrium is established. How much B did you make?
Half a mole.
Half a mole. Have you done your job? No. So you see the kinds of problems that chemists run up against because of equilibrium. How can I get past this problem? Well, That requires an in-depth understanding of the chemistry of this equilibrium system. Maybe the conditions under which you ran this reaction were not the best. Maybe A is cheap. So instead of starting with a mole of A, you start with 2 moles of A, it goes 50%, and then you get your mole of B. But if A is expensive, and you wind up starting with 2 moles of A, which gets you your mole of B, but then have to throw away the 1 mole of A that was not used because the reaction mixture has made it contaminated, the boss isn't going to be happy if A is expensive. These are the kinds of problems which chemists have to fight. In other words, we need to know how to control equilibrium in our favor, so that, as necessary, we can stop the establishment of equilibrium and get this reaction to go to the extent which is necessary to make the amount of stuff which we need to make. Now, this, of course, is a hypothetical case. But we will look at many, many, many real cases as our analysis of equilibrium system proceeds. Now, back to where we were. We looked at a stoppered flask containing water liquid. Shook it up. Upshot of which is that the air atmosphere above the water liquid became saturated with water vapor. Consequence, this condition has now been established: water liquid, water vapor equilibrium inside this flask. How do we evaluate K for this equilibrium constant, given that the equilibrium constant is written as the concentration, molar concentration of water vapor, or the partial pressure of water vapor? Well, we've argued yesterday, and we'll look at this in greater detail as we proceed, that when it comes to dealing with equilibrium systems that contain gases, it's more convenient to refer to the gases contained in the equilibrium system in terms of their partial pressures, rather than their molar concentrations. Why is that true? Because we don't need to pay attention to system volume if we deal with partial pressures and have a way to evaluate such. For this case, we took a look at the water vapor pressure data table that you see on page 21.5 in chapter 21, which is on thermodynamics. In fact, everything we're going to do from chapter 17 through chapter 22 is thermodynamics. And I'll bet everything you talked about in Chemistry 2045, with the exception of the one chapter on kinetics, was thermodynamics. There's only 2 ways to study reaction progress. Did you hear about that in 2045? That's what chemists do more often than anything else. Study reactions and their progress. Because chemists are notorious materialists. That doesn't mean we're evil, bad people. That means we like to make things. And oftentimes we like to make things which are important, or at least have the potential of being very important. Upshot, we're studying reactions all the time. How do we study the progress of a reaction? That's what I'm asking about. There's only 2 ways: thermodynamics and kinetics. And in first-year chemistry, as well as in most undergraduate chemistry, most of the chemistry we look at is from a thermodynamic standpoint, because it's a lot easier than from a kinetic standpoint. The mathematics of kinetics, much more difficult than the mathematics of thermodynamics, at least in most cases. The methodology of kinetics, much more difficult than the methodology of thermodynamics. For example, you can go to the laboratory with nothing more fanciful than what we've done. A flask, a beaker, and establish an equilibrium system in the flask or beaker. We're going to do a lot of that today. Because once the system is at equilibrium, as long as it's not disturbed, its composition remains constant. So you can analyze it at your leisure pleasure. You're not fighting any speed problems, any rate problems. That's what you fight when you're dealing with kinetic processes. A very important kinetic process is the transfer of H+ from a Bronsted acid to a Bronsted base. You looked at this briefly in Chemistry 2045, 45L, Assignment 5, Experiment number 2, or Part 2. You remember that? You know how fast it takes from a kinetic analysis standpoint for H+, say in water solution, to go from a reacting acid to a reacting base, and in so doing convert the product acid and product base? Kinetic studies indicate that this transfer takes place of a single proton in less than a nanosecond. You think that's fast? How much is a nanosecond? A billionth of a second. This occurs in a time that's shorter than a billionth of a second. Now, what kind of problems do you run into if you want to measure this? That's not easy to do. A simple illustration of why kinetics is often a much more demanding and difficult study than thermodynamics. And again, the gadgetry required. Oh, you need some pretty fancy gadgetry to do most kinetic studies. Whereas in many cases, you can do elegant thermodynamic studies with simple gadgetry, beakers, test tubes, flasks, cylinders, the likes of which we do in chemistry laboratory, which you do in 2046L this term all the time, or will do. In any case, let's proceed. I got 2 more flasks, each with deionized water, and we're going to consider 4 systems. The systems will be calcium chloride added to water liquid, calcium carbonate added to water liquid, 1 molar hydrochloric acid solution, and 1 molar acetic acid solution. What we will do in considering these systems is to answer the question, for the systems considered, does equilibrium live in the system involving solute and solution? And if equilibrium lives, what's the equilibrium constant reaction? What's the equilibrium reaction? And if equilibrium lives, what's the equilibrium constant expression? I think by doing this stuff, we'll get ourselves introduced in a rather strong fashion regarding the fundamentals of equilibrium. So let's proceed. First, I got some calcium chloride. Took it off the reagent shelf in the stock room. I'll take a pretty good slug of calcium chloride, a few grams. Put it in there. Recognize that calcium chloride itself is a white crystalline solid. Shake a bit. Let it stand. In a second flask where I've got 300 milliliters of deionized water, about the same as I had in the first flask, I'm going to put some calcium carbonate. Beside being the principal ingredient in teacher's favorite weapon. You familiar with calcium carbonate? You know what's the main ingredient in eggshells? Calcium carbonate, pretty soluble in water. You ever cook eggs by hard boiling them? You ever see the shell dissolve? He shook his head yes. I think he cooks his eggs in acetic acid. That'll dissolve the shell. Let's collect an amount of calcium carbonate which is about comparable to what we had with the calcium chloride. You know that calcium carbonate is the main ingredient a lot of common substances, like crustacean shells, oyster shells, scallop shells. Is there a lot of water in the ocean? A lot of water in the ocean. Well, given that there's a lot of water in the ocean, we might be able to expect to dissolve the shells of these crustaceans. They don't have a whole lot of calcium carbonate in their shell compared to the amount of water we have in the ocean. Yet I'll bet you've never seen an embarrassed scallop or oyster because his or her shell dissolved. Oh, my shell dissolved. See? Well, after vigorous shaking, I can look at the calcium carbonate system and see a bunch of undissolved solid at the bottom. How about a calcium chloride system? All right. So let's take a look at A. For starters, on your paper right now, I want you to write the equation for the reaction that occurred when I put the calcium chloride in water. Because you saw that something happened to the calcium chloride. A white crystalline solid. I put it in about 300 milliliters of water, a few grams of calcium chloride, a little bit of shaking, and voila, the calcium chloride appeared to disappear. A lot of students, when they begin this task, the task being writing equations for reactions, would conclude that I made a mixture of calcium chloride with water. No question about that. So they would write an equation for a reaction starting with CaCl2 plus H2O, which would establish water being a component of this reaction, a participant in the reaction. Did you make that mistake? Is this the equation you wrote? I just wrote water liquid above the reaction arrow just to indicate that it's our solute. Our solvent. But I really don't even need to do that, since when I've written calcium ion and chloride ion, I added the following subscript tag AQ, which tells us this took place in water. How many wrote this reaction equation? How many wrote CaCl2 plus water? How many wrote CaCl2 becomes this? Anybody write this? Now, if you didn't write that, that's good. Textbooks do this all the time. That's an interesting formula, because it represents something that doesn't exist. I don't know why textbooks are in the habit of writing formulas for mythical materials. Materials which don't exist. Yet they do it all the time, general chemistry textbooks. And they wonder why chemistry students have such trouble learning chemistry. Well, what they're offering is junk. In any case, there's a name for this kind of reaction. Do you know the name? We asked you to learn this name in 2045 laboratory. Called dissociation. How many have heard this? I know you've heard the word dissociation. What I want to know is if you've heard the word dissociation applied to a reaction like this. Now, when I say a reaction like this, what's happening in this reaction? For starters, what kind of compound is this, ionic or molecular? How many vote ionic? How many vote molecular? Did you learn in 2045 the generalization that if a formula tells you A compound is composed of a metal and a nonmetal. The metal is calcium, nonmetal chlorine, which of course in this material it's calcium ion and chloride ions. But if I were to bring together calcium and chlorine, you'd see a very vigorous reaction and wind up with calcium chloride. The generalization to which I refer is, if a compound is composed of a metal and a nonmetal, it might be ionic. You heard that? Do you believe it's a guarantee that it's ionic? A compound composed of a metal and a nonmetal? You think that's a guarantee that it's ionic? You think it's a good bet that it's ionic? Now, maybe you can see this periodic table. In any case, whether or not you can see it there, you can all see it here, because remember I commanded you to have this with you all the time. The periodic table on this thing. Take a look at all these materials listed in the families labeled 3B, 4B, 5B, 6B, 7B, 8B, 1B, 2B. And then some of the metals which follow this: gallium, germanium, indium, tin, antimony, thallium, lead, bismuth. Those are all metals. That's a heck of a lot of metals, a heck of a lot of elements. Do you know that those metals, when they react with nonmetals, more often than not form molecular materials? Did you hear that in 2045? I mean, if you didn't, that's okay. But what I want to do is to caution you about the generalization that a formula composed of a metal and a nonmetal is an ionic material. It may be, it may not be. What'd you do to find out? What I'm doing now is hitting at some of the stuff I hope you learned in 2045. But if you didn't, we're talking about it right now. Here's calcium chloride in this bottle. I'll give you each a sample and let you go to a laboratory where you are at liberty to do any and all experiments that you might be of a mind to do to confirm that this is an ionic compound. I'll tell you it's an ionic compound. What would you do to confirm this?
If it dissociates in water.
Well, be careful about this. Number one, how do you know by this system that we created? We put calcium chloride, a white crystalline solid, put it in water, stirred up, the white crystalline solid disappeared, right? How do you know it dissociated?
There's no precipitate.
Well, all right, let's try another reaction. Rather than write the formula, I'll just write this. You familiar with this stuff? You got sugar at home? Sucrose, common table sugar. Is this a white crystalline solid? Yeah. This water soluble? Does this dissociate when you dissolve it in water? You be careful about this. You know, I'm not picking on you. I just want to remind you about how you got to be careful in this chemistry game. All right? So, by virtue of the fact that a compound is quite soluble in water, a crystalline solid is quite soluble in water, in no way guarantees that it's ionic. So we got to do something else.
It's dissolved in water and it conducts electricity. Would that show it's ionic?
Well, now, are you familiar with this stuff? Is this stuff molecular or ionic? I'm asking you.
HCl.
Yeah, molecular or ionic? If I brought some hydrogen chloride in here, I'd have to have it contained in a sealed vessel because it's a colorless gas. If under these conditions which are with us, I have a compound which is a colorless gas, would you suspect that to be ionic? I have a colorless gas compound under these conditions, normal lab conditions. Would you suspect that a colorless gas at normal laboratory conditions, which is a pure substance and composed of two or more elements, therefore it's a compound, Would you expect that's ionic or molecular? I'm asking now if in 2045 you learned about the general properties of ionic compounds. Did you? What are the general properties of ionic compounds? What are they?
Solid at room temperature.
What is that?
Solid at room temperature.
Solid at room temperature. Give me some greater description of this solid.
Crystalline.
Crystalline. How about that? A crystalline solid. Every ionic compound known under normal lab conditions is a crystalline solid. So if I got this compound, which is a gas, it ain't ionic. Okay? And do you know about the conductivity of 1 molar HCl solution?
I guess that's
Did you take 2045 laboratory here?
yeah.
And why are you guessing? You did this work in assignment 4, 2045 laboratory. You know what? I designed 2045 laboratory to feed in the 2046 laboratory. Isn't that rotten of me? What's even worse, if you think that makes me rotten, is I expect that you learn everything that 2045L had to offer. How many can say, yes, I did? Never mind, I won't ask for a show of hands. Chemistry's really tough. And you have to learn on it in a foundational basis. You build, build, build. What you learn today is used to help you learn what you're going to talk about tomorrow, etc., etc. And don't ever take away the foundation. Don't ever, for a chemistry test, say, on test 2, do I still have to know the stuff for test 1? I guarantee if you don't know the stuff for test 1, you can't get any credit for test 2. You won't get anything. Not the way I play the game. Because the game I play is, let's understand chemistry. In any case, I'm not picking on you, we're just having fun. General properties of an ionic compound under normal lab conditions, a white crystalline solid. What would you tell me about the melting points of ionic compounds? Be careful in responding to this. Would you tell me about the melting points of ionic compounds?
Generally pretty high.
Why so?
I don't know, I just think of salt.
But I want to know why the melting point's pretty high.
Because the ionic bond is really strong.
Ionic bonds are very strong. Did you talk about interparticle attraction forces in 2045?
Yeah, I don't remember that. Not that big of a word.
You talked about interparticle attraction forces in 2045, didn't you? The strongest of which is what? What's the strongest interparticle attraction force known? Ion bonds. How about that? Because these things are formally charged electric particles. Tell me in 2045. Did you learn this? You learned this in 2045? Did you? I'm asking. Did you hear about this in 2045? You heard about it. Good. Now what does it mean? I keep telling my 2045 folks, you know, they've all heard about all these things that I need them to understand, yet they don't know anything about them. And I say, what the hell are you doing in this class? They've all heard about electronegativity, nobody understands it. They've all heard about intermolecular attraction forces. They don't understand it. What are you doing? Well, I'll get on with picking on them later. Because understanding is where it's at. All right? Coulomb's law tells us, if you analyze it in detail and do some experiments to go along with it, that tiny particles, are ions tiny particles? If I put an ion in your hand, will you be able to see it? Talk about tiny. Woohoo! Tiny particles which have charges interact with each other electrically very strongly. That's what Coulomb's law says. If the charges on the particles are opposite in sign, they attract each other very strongly. But if the charges are like, they repel each other very strongly. I tell my 2045 folks that from my perspective, Coulomb's law is the most fundamentally important law in the world of chemistry. Because every daggone atom is made up of electrons and protons at the minimum. And these particles interact with each other very strongly from an electric standpoint. All right? So, look at how much we talked about just trying to understand the dissociation process shown by calcium chloride when it's dissolved in water. Now I go back to the question I asked, which was, how can I prove an ionic compound to be ionic? Here's the calcium chloride. Hint, or directive if you prefer, don't proceed by dissolving it in water. That won't get you anyplace. Because every ionic compound, when it's added to water, dissociates. It comes apart into its component ions. That's why the equation for the reaction is called dissociation, because it's a coming apart process. And the component ions, the ions of which this ionic compound, salt, is composed, wind up being in solution. Calcium chloride comes apart into calcium ions and chloride ions. Dissociation. But we're still faced with the task of proving an ionic compound to be ionic. What do we do? All right, I'll give you a hint. We're going to melt a compound. A moment ago I asked you what knowledge you have of melting points in general for ionic compounds. And we recognized that because the ion-ion attraction forces are damn strong, ionic compounds have very high melting points. Because you got to supply enough energy to weaken these ion-ion attraction forces, of which there are countless numbers in a mole of an ionic compound. Before these ions can move in different directions with respect to each other. I just described the molten state for an ionic compound. Now, sometimes ionic compounds don't have a metallic component. You familiar with any ionic compounds that don't have metallic components? A lot of what's going on now is I'm reminding you about the nomenclature that you have to have at your fingertips so that when we talk about ionic compounds, you know what the heck I'm talking about.
Ammonium chloride?
How about ammonium chloride? I'll bet you that's the most common non-metal containing ionic compound. It's composed of ammonium ions and chloride ions. How many of you wrote the formula for ammonium ion like this? H4N plus. Did you ever write the formula for ammonium ion like that? You did in 2045 laboratory if you followed the directions in the lab manual, because I wrote the damn lab manual. I want you to do this right. What's this? What's this? What is it? What is it? Ammonia. An acrid, strong-smelling, gaseous, molecular compound. Now, if I provide a source of H plus to ammonia molecules, per ammonia molecule, one H plus will glue on to this non-bonding pair. I don't bother with dots for non-bonding pairs. They take too long to write. And I'm up here living in a cloud of chalk dust. I don't know the damn difference between a dot and an electron if I use dots. So I don't bother with dots. Only time I write dots is if I'm talking about an orbital that's half filled. A radical. More on that stuff later. But you heard about that too. When H plus comes along, this non-bonding pair converts to a bonding pair and connects to this H. But now I have an ion, because H came along with a charge of +1. So this whole thing has a charge of +1. But tell me, if you look at a Lewis structure, like we have here for the ammonium ion, and the Lewis structure is for an ion, how will you find out where the charges are located in this ion? Formal charge, all right? There's the ion. Everybody do formal charge analysis for this ion right now. I want you to show me or find out for yourself where the plus charge is. Where is it? It's on the nitrogen. How about that? So, if I write the ammonium ion like this, does this show the plus charge on the nitrogen? If I write the ammonium ion like this, where does that show the plus charge? And you also learn, this is part of writing formulas, that when you write the formula for a material, it's standard practice to write the symbols for the atoms of lower or higher electronegativity first. Lower or higher electronegativity. Which symbols are written first in the formula? Is calcium chloride Cl2Ca? Is sodium chloride ClNa? What is it? It's NaCl. Because sodium is electropositive with respect to chlorine, isn't it? Chlorine is much more electronegative than sodium, isn't it? Hydrogen, nitrogen. Which one is of much higher electronegativity? Which one? Nitrogen. So are you going to accept a textbook giving you this trash? Not in this class, you're not. Because that's trash. And I argue this with my fellow teachers. And you know what their defense is? This is tradition. I say, I'm going to tell you what you can do with this tradition when it stands in the way of learning. Learn how to having that in here. This kind of sound like I mean what I say. And guess what? I'm going to back these things up with explanation and reason. Not tradition. That can go straight to hell in here. Unless it keeps with understanding and reason. If it doesn't, I'm not having any part of tradition. All right? Well, we're getting all kinds of places here. We're still on this calcium chloride system. Okay, we still want to find out how I prove this stuff is ionic. I told you to melt the compound. What do we do after we melt the compound? Because I can melt molecular solids just like I can melt ionic solids. Main difference is the molecular solids often melt at a much lower temperature. But then if I start dealing with macromolecular solids, hey, now I'm dealing with materials which will melt at higher temperatures even than ionic solids on occasion. Silicon carbide. You familiar with silicon carbide? Simple formula. Anybody know anything about the hardness of this stuff? Anybody know anything about the uses of this stuff? Anybody do any carpentry at home? Carpentry? Drill bits. When you make a drill bit, would you like to make a drill bit out of sugar? Huh? It's a crystalline solid. How about out of wood? You make a drill bit out of wood? Why not? Those are solids. Why don't you make drill bits out of wood? Why don't you make drill bits out of sugar? Why not?
They deteriorate.
Deteriorate.
Fall apart.
Fall apart. Too soft. Okay? Would you like to make drill bits out of carbon diamond? Hey, those are dandy drill bits. Expensive, but dandy. Why is that true? Why is a carbon diamond drill bit a damn good drill bit? Because it's durable and hard as hell. Just like this stuff. This stuff has a hardness that's comparable to diamond. That's why I make drill bits out of this stuff. When I want to drill holes through concrete, I got to buy expensive drill bits, oftentimes made of silicon carbide. So what kind of melting point do you think this stuff will have? Damn high. So be careful about deciding a compound to be ionic because it has a high melting point. So we're still going this. What the hell do I do to find out if a compound is ionic? I melted it. What do I do now? Next to it, I have some sugar. I melted the sugar. Next to it, I have silicon carbide. I melted some silicon carbide. So I got 3 melts. One's an ionic compound. One's a molecular compound. One's a macromolecular compound. How am I going to test these 3 melts to find out which one is the melt of the ionic compound? Yes! Because in the melt of the ionic compound, I got ions moving around. And ions are electric particles. You think the only kind of electric current is a stream of electrons? No. Ions are charged particles. Any stream of charged particles is an electric current. Any stream of charged particles is an electric current. So if I want to know if a compound is ionic, I make a melt of the pure stuff. And I see the degree to which it will support current flow. And if it does a damn good job of supporting current flow, I got an ionic compound. And that's how I find out. All right. Wonderful. Now let's get back to equilibrium, lest we forget. System. In this system, does equilibrium exist between the stuff I dissolved, which was calcium chloride, and the solution I produced? On what basis can you conclude fairly that this system does not contain equilibrium between solute and solution? Come on, you're looking at it.
There's no more.
There's what? There's no solid remaining. Because if an equilibrium is going to exist, because by now I expect you read this in the notes, you must have quantities of all reaction components, of all system components, all reactants and all products got to be in there. How else could it be equilibrium if you used up all the reactants? Can't be equilibrium. So this one, no EQ, at least not the way by which we prepared the system. No EQ, no equilibrium reaction, no equilibrium reaction, no equilibrium constant. Could I do something to make this become equilibrium? Could I do something, this is our calcium chloride dissolved in water system. Could I do something to make this show equilibrium between solute and solution?
Saturated?
Yes! And how am I going to know when it's saturated?
Keep that until the sun doesn't dissolve.
I'm adding calcium chloride with stirring until
You see some,
I see
some solid.
there's some calcium chloride that has refused to dissolve. Then I know I got equilibrium. Well, guess what? I already achieved that here. Right? So let's get at the calcium carbonate system. B, we know contains equilibrium between solute and solution because the calcium carbonate which I added did not in its entirety dissolve. All right? Now let's start by writing the equation for the dissociation reaction. Do it. On your paper right now. The equation for the reaction that occurred when I put the calcium carbonate in water. Did you write this? Did you write this? Good. That's what you're supposed to write. Okay? At least based on the information which we have before us. Now, what do we recognize? All the calcium carbonate did not dissolve, even though after adding the calcium carbonate, we vigorously agitated the system. So in this system, then we can add this reverse arrow. Because we now know this system contains equilibrium between calcium carbonate, which hasn't dissolved, and solution species, which are calcium ions and carbonate ions. So equilibrium exists in this system between solute and solution. Okay, now then, let's have some more fun with this system. You familiar with this stuff? It says phenolphthalein. You want 2 points for spelling phenolphthalein correctly? Shorthand reference HPHTH. Did you use any phenolphthalein in Chemistry 2045 laboratory? In your previous studies of chemistry, assuming you did chemistry in high school, did you ever use phenolphthalein in high school? Okay. Probably for a titration experiment? Yeah, titration experiment. Okay. What do you know about phenolphthalein? What kind of general name is applied to a material like phenolphthalein? It's an indicator. Well, what the hell does that mean? Tell me.
I think when the pH level changes, it indicates equilibrium.
Indicates equilibrium.
It tells you that point, like the point where there's enough that's dissolved in the reaction as
What reaction?
whichever it's like an acid-base reaction.
Acid-base reaction. So I'll make the statement that indicators in general are used to tell us something about the acid-base nature of a system. Is that fair? I bet you knew that. Did you use any indicators in Chemistry 2045 laboratory besides phenolphthalein? Did you do assignment 5 part 2? Did you use bromethymol blue? You did this, didn't you? And I expect you to have learned from that. Now, I will tell you, and you'll find this out in your Chemistry 2046 laboratory manual, which contains a table of indicators and their behavior in assignment 1. The first assignment you're going to do on page 1-6 in that lab manual. You'll see a table of indicators showing you the pH at which they change color, the pH range over which the indicator is useful, and the different colors which the indicator shows as a function of pH. The table shows you all that stuff. Well, we made 2 systems here. And we've recognized that indicators are used to give us information about the acid-base nature of a chemical system. Let's put some phenolphthalein in this system where I dissolved the calcium chloride. See any color? Let's try this system. See any color? How about that? Now then, shorthand reference. HPHTH, that's phenolphthalein, goes from colorless to red-pink at pH 9.2 or above. You don't need to write this down. That's not important. Okay. Oh my. I'd say that's lipstick red-pink. Wouldn't you? That's a nice, deep, wonderful red pink. Well, interesting, don't you think? To create system A, I dissolved calcium chloride in water. I treated it with phenolphthalein. I see no color change. When I made system B, I just took another ionic compound, this time calcium carbonate. So the difference in the two systems is this one contains chloride ion, this one contains carbonate ion. And this system shows that it has a pH above 9.2. You agree with that? In fact, we'll find out when we go to chapter 19 in the notes, and you'll find this out when you go to assignment 3 in laboratory, that the pH of this system is 10.0 to one significant figure. Why? What happened in dissolving calcium carbonate that's different from dissolving calcium chloride? Clue or directive, I say this now because it will lay foundation for what we will begin to do in detail in chapter 18 when we will talk about acid-base chemistry in detail. Do you agree that our observations force us to realize this system is considerably more basic than this system? More basic? This system has got a pH above 9.2. It's a distinct red-pink. In fact, I just told you the pH is about 10.0. pH of saturated H2O CaCO3 10.0. Well, I should just write it this way. pH equals 10.04. What's pH measured? We actually learned this in 2045 as well. You remember where? 2 assignments related to pH in 45 laboratory. Which assignments were they? I mean, you all took this course. I want to know what you learned. Do I have to make you all take 2045 lab again with me being the teaching assistant? Oh, golly, what a horrible experience that would be. That son of a bitch Horvat is here. Assignment 5, Part 2, as well as Assignment 8, Kinetics. You remember what you did in Kinetics with pH? Or don't you remember doing the bleach experiment? Or I like to call it the laundry experiment, because folks often use bleach to assist cleaning clothes, particularly whites. We want the whites to be nice and shiny white. Ooh. I know my wife is a big fanatic about this stuff. She says to me all the time, "You dirty guy." Yes, dear. Whatever you say, dear. It's quite all right, dear. And she snatches the t-shirt from me that's got a little bit of a soup stain on it. "Have to wash this." "Yes, dear." Well, never mind 2045 for now. What we've recognized is, as we noted before, the pH of the calcium carbonate system is a hell of a lot higher than the pH of the calcium chloride system. And I ask why. And I asked why on the basis of knowing what the heck pH is about. What is pH about?
So hydronium or hydroxide concentration?
Yes. pH measures logarithmically the hydronium ion concentration directly or the hydroxide ion concentration indirectly. You don't need to hurry up and write that down. Believe me, when we get to chapter 18, you'll have that stuff rolling right out of your ears. So we know, because of dissolving the calcium carbonate, because we made each one of these systems starting with the same deionized water, that something from the calcium carbonate caused the pH of this system to be a heck of a lot higher than the pH of this system, which means the hydroxide ion concentration in this system is a heck of a lot greater than the hydroxide ion concentration in this system. And when you get to chapter 18, you'll know that a pH of 10.0 corresponds to a hydronium ion concentration of 1 times 10 to the minus 10, which guarantees a hydroxide ion concentration of 1 times 10 to the minus 4. Now that's not a big hydroxide ion concentration. But 10 to the minus 4 divided by 10 to the minus 10 tells me that in this system, the hydroxide ion concentration is 1 million times bigger than the hydronium ion concentration. A basic system. How did this happen? I don't see hydroxide ion in this reaction. I don't see hydronium ion in this reaction. What's going on here? Is this some kind of mystery?
Does the carbonate become bicarbonate?
The carbonate becomes bicarbonate. There's bicarbonate with the better formula. Because if I ask you to write the Lewis structure for bicarbonate ion and I give you this formula, I'll bet you every one of you will glue hydrogen to carbon, and you'll be wrong. I like to write formulas that keep with structure. Because the most important property of any species by far is its structure. What else do we need in this reaction equation?
The calcium becomes calcium hydroxide.
Oh no. Do you see any? I know calcium ions in there, and I can understand then why you might suspect this produced calcium hydroxide. But what matters is to realize that somehow, some way, by dissolving calcium carbonate in water, because some of it did dissolve, the hydroxide ion concentration went up significantly. And we're trying to figure out how that hydroxide ion concentration went up. And I heard a suggestion that carbonate converted to bicarbonate. Now this in and of itself does not explain the pH observation at all, but explanation of the pH observation is part and parcel of this conversion. What do I need to do to make this an equation? Water. Okay, I got water. You said water, I have the water. Well, what do I do with this water? Tell me. Talk to me.
Well, if you add it to the carbonate, would it also kind of disassociate?
Add the water to the carbonate. Yeah, put some water on the carbonate. Keep going. How about that? And there's how I got the hydroxide ion. Now, under no circumstances would I hold you responsible for this chemistry at this stage of the game. But at the minimum, at least I'm showing you what kind of considerations you have to make as a student of chemistry if you're going to come to grips with equilibrium. This is tough stuff. You have to do experiments. You have to make observations. And from the observations, you have to make carefully drawn conclusions. Conclusions which are sound and which fit the facts. And we're going to guide you through all of this kind of stuff. But guess what? We've just realized that when I dissolve calcium carbonate in water, I get two reactions. I get this dissociation reaction, and I get this acid-base reaction, which accounts for the hydroxide ion concentration production, which accounts for the high pH. Hey. But let's go back to equilibrium, just involving calcium carbonate. And we'll talk about this component of this system later on, not now. Since all the calcium carbonate did not dissolve, this system's at equilibrium, which means we can refer to it with an equilibrium constant. Write the equilibrium constant for this system right here now. How many wrote this? That's it? How many put calcium carbonate in the denominator? Don't do that, because this is a solid, and in an equilibrium constant expression, what do we not include? Solids and solvent. Solids and solvent, or pure liquids. Okay? Only material components of the system whose concentrations or partial pressures change, which means, as we said yesterday, in an equilibrium constant expression, you will find only solute species and gases. That's it. All right, we got K for that. Now, let's look at C. Now, if we did a demonstration for C, our eyeball observations wouldn't be able to tell us anything. We need other methods of observation like conductivity studies and the like. So for C, I'll just proceed by telling you that to manufacture 1 molar hydrochloric acid solution from scratch, I go to the laboratory. I get a source of hydrogen chloride, which is a rather nasty corrosive gas. Colorless, but corrosive. I don't want to breathe this stuff in. I dissolve it in water until per liter of water I have dissolved 1 mole of, per liter of solution, pardon me, per liter of solution I've dissolved 1 mole of HCl. Then I've made this. Okay? Now then, you did this in 2045, assignment 4. Question. In making 1 molar HCl, to what extent did this reaction proceed? How much?
Around 100%.
Around 100%?
100%.
Forget the around.
Complete.
100% complete. %. So, I'm going to draw a picture of another flask. I see a label on this flask. It says 1 cap MHCl. My observations show me that inside the flask is a colorless liquid. If I measure the content, the conductivity of the contents of the flask, the HCl solution, I find out that it's quite conductive. I recognize this reaction goes 100% by this conductivity study. Do you remember doing conductivity studies in 2045 lab? With these very expensive, elegant conductivity meters we gave you? You know, the little thing you held in your hand? Here's the flask. Here's the label. Contents, colorless liquid. For this system, I want you to write its principal system inventory. You recall being introduced to the practice of writing inventories in 45 lab? Why is it important to write inventories for a system? If we're going to do chemistry on a system, is there any way we could possibly understand the chemistry involving a system if we don't know what the hell's in the system? Huh? How can we understand the chemistry in a system if we don't know what's in the system? General chemistry textbooks haven't learned this yet. I don't know what the heck they do. But I can tell you this, as I've already told you, they're not getting inside this classroom. Because they interfere with something called learning. Yeah, I'm not having that. if we want to be able to understand the chemistry that takes place in a system, we damn sure better know what's in the system. And to help us in knowing what's in the system, we write for it a principal system inventory. What's an inventory? What's an inventory? If you work at Publix as a clerk, and the boss comes around and says, well, hands you a scratch pad and a pencil and says, I want an inventory. What are you going to do?
Find out what you have.
You're going to run around a store and make a list of what you got. And if the boss wants the inventory quantified, then you're going to write down how much of each of these things that you got. Right? So there's two parts to an inventory. The first and foremost part is what you got. And in chemistry, we represent what we got by writing formulas, chemical formulas. And if we want to know how much, then what quantity do we usually use to refer to how much? Moles. Well, let's start with the qualitative aspect. For this system, based on this information, I want you to write a formula list right here, which is the principal system inventory for this system. Write it down. Paper, right now. How many wrote this PSI for that system? What else did you write? Or not write? I guarantee, if you're a general chemistry textbook author, and I ask you to inventory this system, you'll write this. How many wrote this? You got a red pen? If you got a red pen, take this formula and do this to it. This is a lie. There are no HCl molecules in that system. They all reacted, right? Didn't this thing go 100%? So textbooks can write this junk on their pages all they want. It doesn't make it real. It doesn't make it exist. And it certainly doesn't show this to be a component of the system because this ain't there. How about that? We want to deal with what's real. Ain't that something? That's what science is about. Dealing with what's real. General chemistry textbooks have a habit of not dealing with what's real. Because of, guess what? Tradition. They can build a big bonfire of this tradition. And I'll be the first to put the gasoline on it and the first to put the match to it. That's where that stuff needs to go. Because it interferes with learning. And we're not having that. But I've said that before, haven't I? You think I'll say it again? There's the PSI for this system. These are the main ingredients of this system and nothing else. Now, next question. For this system, does equilibrium between solute and solution components exist? Do I write an equilibrium constant for this system? The answer is no. Why not? Because there's none of this left. That's why I don't write an equilibrium constant, because there's no equilibrium existing. Now let's look at the last system. Do you recall that this is shorthand abbreviation or reference to acetic acid? The correct formula for acetic acid, as well as I can write it, is this. The Lewis structure for acetic acid which corresponds to shape is this. So you got to be careful with formulas like this. You'll see this in organic class all the time, because you at this stage of the game would probably think that writing this formula means you got an oxygen-oxygen bond. And I wouldn't blame you for reaching that conclusion. That's what the formula suggests. That's why you got to be careful with writing these formulas. But there is no oxygen-oxygen bond in this molecule, as this Lewis structure shows you. But never mind the Lewis structure for now. What counts is to realize that this formula is shorthand for this stuff, which has this structure. And when this reaction takes place, as in this reaction, C, I started with a molecular material, I combined it with a molecular material. These materials as pure stuffs are lousy electric conductors. But when I put them together, I have a system which is a marvelous conductor, because this system is very effective at creating ions, chemically creating ions. So I don't call this dissociation, I call it ionization, because we made ions. That's what ionization means. So for this reaction, I'm also going to call this ionization, as opposed to dissociation. But I need to realize one big difference. This molecule, like the hydrogen chloride molecule, reacts with water to make hydronium ion. That made chloride ion, this makes the acetate ion. But when this reaction goes in making 1 molar acetic acid, this reaction goes a whopping 0.4%. Does equilibrium exist in this system? Between solute and species produced by dissolving? You betcha. So what's the equilibrium constant? Write it. K equals hydronium ion molarity times acetate ion molarity divided by the acetic acid molarity, because in this system there is a huge concentration of residual acetic acid. In fact, it's still 1 molar to one significant figure if only 0.4% of it went away, because 99.6% of it is still there, which to one sig figure is 100%. So here's my equilibrium constant for the acetic acid system. Last question. For the acetic acid system, 1 molar, I want you to write the PSI. Because if we're going to do any chemistry with acetic acid solution, and we're going to do this quite often, you'll do this quite often in the laboratory, we've got to start by knowing what the heck's in the system. The principal species inventory for 1 molar acetic acid, given that this reaction goes as written only 0.4%, and then equilibrium is established. Everybody done? How many wrote this? Acetic acid and water. Those are the principal species. Nothing else. Why is that true? I told you. This thing, as written, goes 0.4%. So 99.6% of these things are still there. They've retained their structural and molecular integrity. So the main ingredients of this system, after the system has been prepared, is solute acetic acid and water itself, and that's it. So I hope at the minimum, after we've gotten together now just 2 times, you've recognized we not getting any place if we got to learn science by I give you information and you give me the information back. That means nothing. What counts is understanding, and that's where we're at. All right? Tomorrow.